In the last few segments under bending, we discussed about how a beam of uniform cross section bends or deforms under pure bending. In fact, we also discussed about the stresses that get developed under such conditions. But all those analysis or discussion was in a qualitative way. We never talked about how much. We said how, in what way, what will be the nature of those deformation, those stresses, but we never talked about quantities. So that was a qualitative discussion, and in this segment we will move towards quantitative discussion about those deformation and the stresses. And in this segment we will be talking about the strains that are produced under pure bending, and in the next segment we will be talking about the corresponding stresses. As soon as we and these values we will see in terms of the geometric parameters of the beam and the moment that we apply, because these are the two things which will affect the developed strain and stresses. So let us start that. So till now we have seen that say a beam is say bent like this. Okay, and maybe it's, and then we discussed why it should be the shape will be part of a circle, an arc of a circle, and suppose, and then we also talked in a qualitative way why some part will be, in fact the upper part of this beam will be under compression and the lower part will be under tension. We do not know where the transition from compression to tension will happen, but somewhere it will happen, and where it will happen, it depends on the geometry of the cross section. We will see. So that is what I mean by quantitative. Now where it will happen, we will calculate that. So yeah, and then one more point, because this cross section is a uniform cross section, no material changes, no area changes, sudden area changes. So that means the stresses also will be continuous, and that means somewhere even the strain will be 0, the stress will be 0, because we know that if a continuous function moves from positive to negative over some domain, so it must pass through 0, right. So mathematically we can say that. So that means if these are under compression and these are under tension, somewhere there must be a fiber which is neither compressed nor elongated. And let us assume that that is somewhere here. Okay. We do not know where the exact location is, but let us assume it is somewhere, and we will denote by rho the radius from the center of curvature to this fiber, which we call the neutral fiber. Neutral because neither it is extended nor compressed. Okay. And let us say this angle of the arc that subtends at the center be theta. Now let us consider another fiber which is say at somewhere here, and what we will do, we will define a coordinate system whose origin is at this location, for example here, like this, say x, y, and the z axis is coming out. And so if we see here, so the x axis is like this, the y axis is like this, and the z axis is coming out. So that is the coordinate system we are referring to, and then this distance then of this fiber, which we can call a test fiber, which we are now considering, is at a distance of say y from the neutral axis. Okay. Then what will be the strain that gets developed on that fiber? That is what we are trying to now quantify. Now, if this is the neutral fiber, so let me give some names also. Maybe this is say AB is the neutral fiber, and CD we are considering, which is under compression because it is towards the upper side. And then when I say upper, that means according to this diagram, and the beam is concave upwards. Okay. So now the length of AB, suppose that is a L, is what? Rho times theta, right? But then this distance is how much? This distance is now rho minus y from the center to the fiber under consideration. Now, if that length, the length of that fiber is now L prime, it's rho minus y times theta. Okay. But now, before we bent the beam, this fiber CD also was of this length AB, means L prime was earlier of length L prior to the application of the moment or prior to the bending. So that means now the change in length, so I'll call say delta will be L prime minus L, which is nothing but say rho minus y times theta minus rho theta, which is equal to what? Rho theta will cancel out, minus y theta, right? If that is so, so that is the change in length of that particular fiber CD. So I'll say that delta of CD, right, L dash of say CD, L is say AB, and LAB was the length of LCD prior to application of the moment. Okay. Now that means then I'll say that the strain which got produced in the fiber CD is equal to what? This length minus y theta over its original length, which was rho theta, right? So that means it's nothing but negative of y over rho. Fine. Now, if so that tells us, and then so please note this negative sign here. This is important. It tells what? Y is positive towards the upper side and then starts at the neutral axis. That means when y is positive, you are getting a negative sign because rho is positive in this direction. Concave upward curvature is called positive. So that means this is negative, the strain is negative. That means all the fibers which are towards upper side of the neutral axis are compressive, the strain is compressive. And if I go downward, the y will become negative, and so this term will by default will become positive numerically, and that will give us the tensile strain. Okay. So that's what is the meaning. And then observe, in fact to observe that, what we can do, let's say uh, whatever fiber, because see this one, because it depends on this factor y, its numerical value, its absolute value will be maximum whatever side is farther from the neutral axis, whether the compressive side or the tensile side, we do not know now. It will depend on the nature of the cross section, but whatever it is, whatever side is farther from neutral axis, on that side the strain will be maximum. And let us say that strain we call say epsilon m, which is nothing but it's maximum, absolute maximum value, if that is C over rho. Okay. So please, this C is just a name, this is the distance from this. Okay. So this is the maximum distance of any fiber from the neutral axis. In some cases it could be on this side, in this particular case is the way I have drawn, it is on this side. Okay. So yeah, so this is suppose the maximum absolute value, then we can write the epsilon or the strain at any location. Okay. And this strain is in the x direction, because all these things we consider the x axis to be along the undeformed axis. So epsilon x, that we will call epsilon, that is the strain in the x direction, will be equal to say what y, so minus y over c, this c times epsilon max, right. So just this radius of curvature we just eliminated from these two equations, so that this is the relationship between the maximum strain that develops and the strain at any location. And so this is very similar to the strain which we, or the expression for strain we derived for the torsion case, if you remember, and we express that in terms of the maximum strain or stress that gets developed anywhere on the cross section. So what it tells you now is, wherever now let us say how the distribution will be. Y is equal to 0 at on the neutral axis, so obviously strain is 0, and then as we move in this direction, linearly this value increases, because once we go to this extreme fiber where y is equal to c, the strain will become the maximum strain E epsilon m, and if we go the other side, it will become negative value. So the strain will be positive, and it will be some fraction of the maximum strain that gets developed on the other side. So it tells everything, but in terms of epsilon m, that is the maximum strain. And so what we will do in the next segment, we will use this distribution of strain along with the equilibrium equations to derive the relationship with the applied loads, because now till now, see here we have only the properties of the cross section. Till now we in this expression nowhere we are seeing any effect of the load that we have applied, right. And so this only tells that how it will be distributed with respect to its maximum value. Now what will be the maximum? It will come from the applied load plus the geometry also. So that point needs to be kept in mind. Okay. So we will stop here for this segment, and we will see the stress distribution in the next segment.